Welcome back to the deep dive, where we peel back the layers of infrastructure to reveal the extraordinary complexity just beneath the surface.
Yeah,
Today, we're moving far beyond typical construction into a really specialized world protective engineering rehabilitation, and we're focusing on a critical project in the Kingdom of Saudi Arabia.
that's right. Our subject is a company called Malak Al Injaz Contracting, or MAICC, and we have a deep stack of sources today.
What are we working with?
We've got their full company profile, which is interesting, but crucially, a highly detailed technical report. This thing documents the surgical restoration of an underground water tank in Al-Khobar.
So our mission isn't just about the who, it's really the how. We want to uncover the specific technical methods needed to, stop structural failure, arrest active leaks, and make sure this thing can safely hold potable water for years to come.
And just for context, MAICC is headquartered in the Eastern Province. With over a decade of really focused experience, they're not a general builder.
They're a specialist?
Exactly. They're an asset preservation specialist working across infrastructure, industrial, even governmental sectors in KSA and the Middle East.
Okay, so let's unpack that. What's the core philosophy that lets a company take on a job this intricate? I mean, failure here is a public health risk.
Well, their operations are built on 4 pillars. The first one they talk about is excellence.
Which means?
It means superior craftsmanship, rigorous quality control, and just adherence to international standards and the Saudi building codes.
That sounds non-negotiable in this field.
It is. The second pillar is innovation, constantly looking for cutting-edge tech, sustainable practices. You can't really fix an old structure with old techniques if you want it to last.
Makes sense. Then there's reliability.
All right, timely delivery, sticking to the budget, which is just vital for any big infrastructure project. You can't afford delays.
And the last one is integrity. So the whole process has to be transparent, ethical, and, fully compliant.
And connecting those pillars to the actual engineering is where the value is. That specialization is what separates them from a general contractor. They focus on 5 key services that directly address durability in a harsh environment like KSA's.
And I'm guessing these are crucial to understanding this Al-Khobar project.
Absolutely.
Okay.
So first, high-performance waterproofing systems, the shield against water getting in. Second, thermal insulation, which is engineered for that extreme climate for energy efficiency.
Okay.
Third is industrial-grade protective coatings, so resistance to corrosion, chemicals. And the last 2, concrete injection and concrete repair. That's the structural surgery they perform to stabilize failing assets.
The doctors for aging infrastructure. I like that. So this is where it gets really critical. Let's shift to that Al-Khobar water tank. It's underground, reinforced concrete, absolutely vital. What state was it in before they started? What were the symptoms?
The site assessment was blunt. It said the structure needed a full structural repair, leak arresting, and potable-grade waterproofing system. The tank was basically failing, comprehensively.
Give us some of the specifics. What kind of structural damage did they find?
They found significant defects. And this wasn't just, hairline cracks. They found both static cracks, which are stable but still a weakness, and active cracks.
Meaning they're still moving?
Exactly. Widening, moving due to load or thermal stress. And they were all over the walls and the flooring.
And the report mentioned something called honeycombing. What is that, and why is it so bad in a water tank?
Honeycombing. Yeah, that's a serious defect. It means you have these voids, this porosity in the concrete. It happens when the cement paste doesn't fill all the gaps between the aggregate when it's poured.
So it's like a concrete sponge.
Pretty much. And for a water tank, that's a disaster. It means water has an easy path to get in, corrode the rebar, and get out.
So you've got weak points, you have active movement, and porous concrete. Was water actively getting in?
Oh, yeah. It was an immediate problem. You could see active seepage along the crack lines, dampness everywhere, and minor but constant dripping where the walls meet the floor.
And when water is actively flowing, you can't just slap a patch on it.
No, you need an intervention that can chemically fight back against flowing water.
And I imagine contamination is the final piece of that puzzle. That's what turns it from a structural problem into a public health liability.
Precisely. The inside was heavily contaminated. They found latents. That's a weak, chalky layer on the surface dust. And critically, algae and biological growth from all the moisture.
And you have to get all of that off or nothing new will stick.
It compromises adhesion instantly. Has to be completely stripped away.
That makes the material selection just Absolutely critical. You're moving from demolition to restoration, and everything has to be non-toxic, certified for potable water.
So what were the MVPs in their toolkit?
They had three main specialized materials. For those active leaks, the flowing water, they used a hydrophobic polyurethane injection resin, a PU resin.
How does that work? How does a resin stop flowing water? It's a bit of a chemical marvel, really. When this resin hits water, it reacts by expanding fast. It seals the voids and the cracks from the inside out. It basically creates an immediate flexible plug deep inside the concrete.
So it stops the flow so you can work on the actual structure.
Exactly. It lets you proceed in dry conditions.
Okay, so the water is stopped. Now you have to replace the weak concrete. What did they use for that?
They specified a high-strength structural repair mortar, specifically a polymer-modified, fiber-reinforced, non-shrink Class R4 mortar.
We hear R4 a lot in these specs. For anyone listening, why does that class R4 matter so much?
That R4 classification is critical. It confirms the material meets really stringent requirements for strength, load-bearing capacity, and durability. And the non-shrink part is non-negotiable.
Because it would just pull away from the old concrete, right?
Right. It would create a new gap, a new path for failure. The fiber reinforcement adds tensile strength, making the patch a cohesive part of the structure, not just a plug.
And the final barrier. The thing that guarantees the water is safe to drink.
That was the two-component cementitious elastomeric coating. It's designed to be like a flexible skin. It's cementitious, so it bonds really well, but it's elastomeric.
It can stretch.
It can stretch and bridge micro cracks without tearing. And of course, it's certified safe for contact with drinking water.
Breaking down the actual steps really shows the complexity here. This is like high-stakes surgery. What was the absolute first step?
Surface preparation. If you fail here, everything else fails. Period. They had to get it clean both mechanically and chemically.
So what does that involve?
Mechanically, they removed all the old stuff plaster, bitumen, any loose concrete. Chemically, they used high-pressure water jetting. We're talking 250 bar or more.
That's not a power washer from the hardware store.
No, not at all. This is designed to strip away that weak latens layer and open up the pores of the good concrete underneath. It maximizes the surface area for the new materials to grab onto.
And what about the steel rebar they would expose during all that cleaning?
Any exposed steel. The skeleton of the tank gets treated immediately with a zinc-rich primer. That's corrosion mitigation 101. If you leave it exposed, rust will start, it'll expand, and cause new cracks down the line.
Okay, so the canvas is clean. How did they tackle the concrete repairs, starting with those active leaks?
This is where precision gets really important. For the active leaks, they did crack injection. That means drilling holes from mechanical packers into the concrete at a 45-degree angle
Why that angle?
to make sure the hole intersects the crack deep inside the structure, not just on the surface.
Drilling precise holes at an angle in a confined space, knowing you're about to pump in high-pressure resin. That sounds risky.
It's very high risk. It requires specialized training, constant monitoring of the pressure gauges, and immediate cleanup. It's a real trade skill. But once those leaks were stopped, they can move on to the static defects.
Stable cracks and those old tie rod holes.
Exactly. For those, they open them up into a V-groove shape. That V provides a kind of mechanical key. It locks the new repair material into the old concrete. Then they fill them with that high-strength R4 mortar.
I want to pause on the fillet formation. That 50 by 50 millimeter chamfered angle they build where the wall meets the floor. Why is that step so critical?
It's all about managing stress. A sharp, 90-degree internal corner is always a zone of maximum strain in a structure. As the tank fills and empties and heats and cools, all that stress concentrates right there.
And it would tear the coating.
It would. So by creating that polymer-modified fillet, they soften the corner. They distribute the stress over a broader area. It's absolutely foundational to making sure the waterproofing system succeeds long-term.
That attention to detail is amazing. Now we get to the final protective layer, that specialized skin for the potable water.
And this step demands a very specific starting condition for the concrete. They call it saturated surface dry, or SSD.
Saturated surface dry, what does that mean in practical terms?
It's not just damp. It's this exact moisture point where the concrete's pores are saturated, so it won't suck the water out of the new coating. If the concrete is too dry, it dehydrates the coating and weakens it. Too wet, and it dilutes it. Getting the SSD is non-negotiable.
Once they hit that condition, they apply the first coat of the coating horizontally. But there's more to it, right? This is where the reinforcement comes in.
Correct. And this is arguably the most important physical feature of the whole system for long-term crack resistance. the alkali-resistant fiberglass mesh.
So it's like rebar for the coating itself.
Precisely. They embed this mesh directly into the fresh first coat. They focus it on all the corners, the junctions, and critically, over every single one of those crack repair zones they just patched.
So if a microcrack forms underneath later, the mesh holds the membrane together.
It gives the membrane the tensile strength to bridge that crack without rupturing.
And the final application.
The second coat goes on vertically, usually after the first is set for a few hours. The goal is a final dry film thickness, a DFT of at least 2.0 millimeters. That DFT is the measurable protection. It's the insurance policy.
And the job isn't done yet. You have to cure it properly.
Absolutely. The whole system is cured for 5 to 7 days. For the first 48 hours, they apply a continuous mist cure. That prevents the surface from drying out too fast and ensures the coating develops its full strengths and flexibility.
So after all this intensive surgery and this high-tech skin, how do we know it actually worked? There has to be a definitive test.
The standard is mandatory and rigorous. The 72-hour flood test. They seal the tank, fill it completely to the overflow level, and then they watch it continuously for 3 full days.
3 days of sustained pressure on every single repair. And what did the final report say?
The report confirmed the system was successful. Status: passed and approved. The critical findings were twofold. 0 leakage observed on the outside surfaces.
The water was contained.
And no drop in the water level inside the tank, other than, natural evaporation. It validates the entire methodology.
And this isn't just one company's method. It aligns with global standards.
Absolutely. The process followed key international standards, ACI standards for crack repair and protective treatments, ASTM for adhesion testing. It confirms the solution is globally recognized as sound. The big takeaway is that this tank now meets all the requirements for safe, long-term potable water containment.
So wrapping this up, this project just shows that maintaining infrastructure is so much more complex than building it in the first place. This was structural surgery with advanced polymers to guarantee an essential utility.
And it isn't a fix-it-and-forget-it solution. It requires vigilance. The final report actually mandates routine inspections every 6 to 12 months. And they stress that the waterproofed areas have to be protected from future mechanical damage, like someone dropping a tool inside.
Right, protecting that 2-millimeter layer. So we've seen the extraordinary technical precision and material science needed just to repair existing infrastructure and guarantee water safety, which is essential to public well-being. The question this raises for you, our listener, is this. We saw that every single structural flaw, from honeycombing to a simple 90-degree corner, had a specific, sophisticated engineering countermeasure. So how often do the structures we rely on every day, our roads, tunnels, storage facilities, require this level of invisible, complex rehabilitation just to maintain their basic function and safety? That's something to think about until the next deep dive.